All right, today we're going to pull back the curtain on something invisible, but it's something that shapes pretty much everything around us. It's a mathematical key that unlocks the secrets of sound, light, and so much more. Let's jump in.
So think about this for a second. What on earth could a quiet concert hall, a medical ultrasound, and your Wi-Fi signal possibly have in common? I mean, they seem totally different, right? Well, it turns out they're all connected by one single hidden principle.
Getting that perfect sound in a concert hall, where every single seat sounds amazing with no weird echoes or quiet spots, that's a massive challenge. It's all about engineering sound waves just right.
Or how about this? A doctor using sound waves, these high-frequency vibrations, to literally see inside your body. They're turning something you can't see into these incredibly clear, life-saving images.
And then there's your Wi-Fi signal. Just think about it. It's this complex, invisible wave that somehow has to find its way through walls, furniture, you name it, just to give you a solid connection. It's honestly a little bit of magic, a true marvel of engineering.
So the secret that ties all of this together, it isn't some thing, it's an idea. It's basically a mathematical master key that lets us understand and even control all these different kinds of waves.
And here it is, folks, the Helmholtz equation. Now, I know, it looks super intimidating with all those symbols, but stick with me because the core idea is actually pretty straightforward. That little triangle thingy, that's just describing how the wave is changing in space. And that K, that's all about the wave's specific frequency. We're going to break it all down, promise.
Okay, so here's the best way to think about it. Imagine you're trying to study a wave out in the ocean. It's always moving, right? It's changing, it's messy, it's complicated. What the Helmholtz equation lets us do is hit the pause button. It's like taking a perfect, high-resolution snapshot of that wave at one exact moment in time. It turns that chaotic, moving picture into a simple, static map.
And this isn't just some random math exercise. It's actually a really clever shortcut. You see, scientists and engineers were staring at this huge problem of waves changing in both space and time, and they came up with this brilliant trick to make life easier.
So, here's the game plan. They start with the big, complicated general wave equation, the one that describes pretty much all wave motion. Then they do something really smart. They say, okay, what if we just focus on waves that are humming along at one single steady frequency? And when you do that, poof, the whole time part of the problem just drops away. And what you're left with is our new best friend, the much simpler and actually solvable Helmholtz equation. It's a total game changer.
All right, so we've got this map of a wave. So what? Who cares, right? Well, this is where it gets really cool. Let's connect this abstract math idea back to those real-world puzzles we talked about at the beginning.
Okay, let's head back to that concert hall. If you want to control how sound waves bounce around the room to make everything sound perfect, you can't just guess. You need a blueprint. You need a map of exactly how those waves are going to act in that specific space.
And that's exactly what this equation gives us. By solving it, acoustical engineers can literally map out the sound fields. This is how they design those amazing concert halls, create totally soundproof rooms, and even use sonar to find a submarine deep in the ocean. It all comes down to mapping those sound waves.
But wait, there's more. It's not just for sound. The exact same equation that maps out sound can also map out a completely different kind of wave, electromagnetic waves. And yup, you guessed it. This is the science that makes your Wi-Fi work.
So engineers use the Helmholtz equation to figure out exactly how the radio waves from your router are spreading through your house. This helps them build better antennas. But it's also totally essential for your cell phone signal, for developing lasers, and even for medical tech like MRI scans, which also use radio waves to see inside our bodies. And the reach of this equation is just incredible. It goes from the airwaves all around us right down to the actual ground beneath our feet. In geophysics, scientists use it to understand these massive, powerful waves that travel right through the planet.
Think about it. When an earthquake hits, it sends these huge seismic waves rippling through the Earth. By mapping how those waves travel, scientists can figure out what the Earth's core is made of. They can pinpoint exactly where an earthquake started, and they can even find hidden pockets of oil and gas.
Okay, so we've seen all these incredible applications. Let's zoom out a bit and get to the real heart of it. What is it that makes this one little equation so unbelievably powerful?
This right here, this is the genius of the whole thing. On one hand, you have the general wave equation. It's dynamic, it's describing waves moving through time, and honestly, it's a huge headache to solve. But on the other hand, you have the Helmholtz equation.
It makes this brilliant trade-off. It says, let's forget about time for a second and just focus on the wave's shape in space. And suddenly the problem becomes static. It becomes solvable. It becomes a map we can actually read.
And that, right there, is the crucial takeaway. The Helmholtz equation is more than just math. It's a perfect example of a core strategy in science. When you're up against a problem that seems way too complex to handle, you find a way to simplify it. You make a clever sacrifice. In this case, you sacrifice time to get a solution that's incredibly powerful and useful in the real world. It's how we take something chaotic and turn it into something we can understand and control.
So, from making a symphony sound perfect to connecting the entire globe, this one powerful idea has given us the tools to master the unseen waves that shape our modern world. And it really makes you wonder, doesn't it? What other invisible forces are out there, right now, just waiting for us to find the right map to finally see them?